let's talk about main drivers and how we can analyze them and write a good report using R. Now, the first thing to notice is we're inside of an RMD file. That means R Markdown, which gives us the option to knit the file into HTML, PDF, or Word. You can actually make an HTML and just put this online for people to view, or you can knit it to Word and print it out, or PDF. A lot of times you'll see us coding inside of an R script. That's why I have a billion untitled R scripts, because I'll just open one up. This doesn't have the knitting options. It's just a script of code. So preferably, if we're going to present something, we might put it inside of an RMD, R Markdown file, which then has the Markdown capabilities to be knitted. Don't change anything up at the top here. You can, when knitting, change it to Word, and it'll do it for you. So one thing a lot of people don't know about is you have the ability to go through an RMD file if you put either chunks or you put little hashtags. With the hashtags right here, you can go right to them in your document. With the chunks, you can even label your chunk. We'll call this Brian's Fave. It can be a little bit iffy with certain characters you put in chunks, so I'm a little bit against writing in tons of stuff, but if we click away from this and we go down below ROI, we should see below the ROI, Brian's favorite chunk. Now, it's just whatever you want to name the chunks. Also, you can't give them the same names, but it's easier to kind of tell where your chunk is at if you label your chunks and you go here for movie analysis. Once again, there are some characters that are not allowed in these, so be very careful while doing this. If you make an error in the way you're typing these out, then you will have a problem with the chunks knitting. So sometimes you create an error with this, and it will create an error later on. So let's go back here and start at the top of the file. So with this, the first thing we usually do when we start out a file is load up our libraries. You've got Tidyverse right here, which loads in a bunch of different packages from the Tidyverse. You see right here, dplyr, that's the real one for data manipulation. Forcats, that's for categorical variables. ggplot2 for graphics. Lubridate for dates. Per, I always forget what per does, so one of the packages I don't know. We could probably type question mark per right here and figure out what it does. It's going to tell us over here, function programming tools. That's great. Can learn more about that. Readr for reading in files, stringr for dealing with strings or characters, tibble for making nice tables, and tidyr kind of brings it all together. Conflicts lets us know if two functions have the same name, they have what's called a conflict, or they mask. Think about a mask as something you put over something, your face usually. And with this right here, you'll notice if I type in filter, filter comes out of dplyr. To get to the filter from stats and run it, I have to do what it says up there and go to stats, : and go to filter. And now I can use the function filter that's in the stats library. Also, the same thing would be for lag. So you don't usually want to load in all your libraries. You just want to use the ones you're going to use because you'll get a lot of conflicts. Red class right here is going to load in it right now. All the red text is not bad, but you notice we have another mask where combined is going to be taking over from dplyr. So if I type combine right here, I won't get the dplyr version. I'm getting the reg or the random forest. That came from random forest package right there. So red class loaded in what's called required packages. Required packages are packages that are also being used by red class that is required to load when it loads. And one of those required packages had a function of the same name of a function inside of dplyr, and thus now the combine function is now the random forest combined and not the dplyr combined. Once again, to get to the dplyr combined, if we ever want to use it, we have to now type dplyr and type : combine to get to the masked function. Just very important to know what all this means as you go through it. We're going to load stringr right here, which has already been loaded in, multi-comp view for creating connecting letters reports, and last but not least, a rules for also making market basket analysis or other types of analysis. So now that we have this right here, and we'll correct this, look at this, we can correct typos. This is not something you could do in R a long time ago, but there you go, typos corrected. I was here before R had typo correction. The source function is really great for loading in sources. And the first thing we're gonna do right here is basically save a URL. My common way of doing this is to type URL, but you can do my file path. Right here, the name is just a naming convention to store this URL, and it needs to be in quotes because it's a string. You'll notice the URL has now been saved to the top right corner. It's just a string of words. Now the source is gonna go there and read in and use it and give us the functions that are at that, and it is called a GitHub gist. So the functions from the GitHub gist. So really cool that someone can just put their functions online and we can get these main driver helps right here. Examine driver for the Y categorical variable, examine driver for the Y numeric variable, replace rare levels. And the my file path at this point, technically speaking, this is not required, but we could go remove my file path if we just want to declutter the global environment. Not required, but you can always do things. So with this right here, source is really great. It could also be a local file on your computer. You can use a source just to load in things. It's just going to load from that and run that. So really great option right there, as via the example, to use a URL or to do it from a file on your computer. So here's the functions we have right here that we just got in. Replace rare levels. A lot of times categorical variables have tons of levels. And let me just tell you, 320 will probably be using this function right here to help clean up categorical variables that are just so messy. And so rather than do it ourselves, we can oftentimes use a function that knows how to do it for us. And it's just coded by someone who figured out a way to clean up the levels. So you don't want something with like 500 levels. You want something nice and neat, 10, 20, maybe 30. Depends on the data, depends on the size, depends on how rare the levels are. Examine the drivers of the Y categorical variables. This is going to help us analyze a main driver for categorical responses. Maybe we're predicting if a movie is a success or not a success, then that's going to be a categorical Y. And the other one, the Y numeric, if we're predicting ROI for a movie, we need to use the function examine driver for a Y numeric. So the key difference right here is, are you predicting something like, does somebody drop out of college? Y cat. Are you predicting something like, what is someone's GPA? Y numeric. Are you dealing with a categorical variable when making predictions that has way too many levels? Replace rare levels. So let's start looking through our data right here. Make sure to go to Canvas and download the case4-moviesuccess.csv. You have to know every bit of this. I always say to people, read your code as a sentence. Movies is what we're saving into. Save into movies by reading the CSV file that has the name. There's the name. The next bit of code right here is strings as factors is true. That means when we read this in right here, you'll notice it doesn't say string over here. If you put this to false, which can also be a 0, you'll see it's characters. So we don't want characters because that's what a string is. It's just characters. You can replace this with a 1 now because 1s and 0s are trues and falses just by 1 and 0. So we want it to recognize the words as levels. Now we're going to write here, and we're actually going to change the title because notice how many factors there are. We're going to change the factor back to a character. There was only one we didn't want to be a factor. So with this right here, we now have our data cleaned up a little bit. And one of my favorite functions to use right here is glimpse. Not flimps, but glimpse. Glimpsing lets you look at stuff. What's really great about glimpse over str, which is structure of data, structure can create a messy look at the bottom of the screen, but when you run glimpse, it's gonna go to the size of the screen. So if you have a big screen, you get a big view. You have a small screen when you run glimpse, we'll go to the very bottom, it goes to that size. Actually, that was so small that glimpse couldn't even do it. I've never seen that. But glimpse usually tries to go to the size of the screen, so when you run glimpse, you get a glimpse of your data. We'll clear the bottom out right here and rerun it and glimpse what's going on. There's our data. 2,225 rows of movies. Got Cloverfield, 10,000 BC, 101 Dalmatians, hashtag alive, the ROI of the movie, the rating on Tomato Meter, the IMDb, the year, the month, the week of the month it came out, the budget, the runtime, the MPA rating, the main genre, the secondary genre, the number of genres it's in, the main actor, John Goodman, Frank Welker, Glenn Close, 101 Dalmatians, main actor in IMDb, and then main studio, main director, original language. So a lot of this might be part of the main driver on why a movie has such a big ROI. And what is ROI? Return on investment. Basically, people want to make money on movies. And if you have a negative ROI, that's not good. That is not good. Let's look a little bit more at the data more in depth. So one thing we want to do is we want to figure out if there's missingness. When it comes to missingness, that means no values there. What does no value look like? Well, let's see if there are no values. What is this code doing? Well, here's all the IMDb ratings. Bunch of ratings. Next, we have, is it missing? So when you run an is dot on something, it's a logical check, and it sees if something meets the criteria for the logical check. Is it missing? If you see a true in here anywhere, and we have a lot of rows, oh, we found one of the only 5. So that is missing right there. So if we went to the movie data and we went to row 450, 460, I believe that is, we should see missingness at row 450. So this is going to be an adventure. We're going on a field trip right here to row 460, down to 460, almost there. Here we are, and there it is, missing. That's what we found, and that's what it meant in the data. There's quicker ways to do this, though, if you change it to which. 460, ooh, there was one at 214 also. So we missed that one as we were scrolling through, but which gives you the positions of the trues in a vector. And let's put some notes on this, because we should know some of these commands right here. Sum right here is going to find out total missing, because we're just adding up all the amounts of missing, whether it's true or false. Because when you add a logical vector, trues are 1s and 0s are falses. And thus, if you add up all the trues, you will find out there are 5 trues in here, and which tells you the positions of the trues. So positions of missingness. So those are the positions of the missingness. Better yet, one of my favorite things is to store it to rows. And what I would do right here is figure out a subset of the missingness by going into here to our movies and go to the rows. And here's the movies that have missingness. So it is Beauty and the Beast, Dog, Monster Hunter, The Box, and The Wave have missingness for their IMDb rating. So why? I don't know. So here we are, making a data frame of the missing movies, as you can tell. And this is how we make our own data frame by hand right here. So notice what you see right here. Missing ratings is the movie data frame that we have. Data.frame calls the creation of a data frame. Now you see right here title. And title is going to be the first vector. The reason we go to more spaces is because it's going to look really long if we don't space it out. So take a look right here as I space it all out. That is the first vector in the data frame. So with the first vector right here being title, the next vector is IMDb rating. And this is just a smaller version of the data with only the movie names and the IMDb rating. A lot of ways to do this, though, and this is what we like to point out. Can you think of an alternative way to make this from the data? Well, remember what I did up here. I have which rows are missing. Well, I stored that as rows so I could find the rows. If I only want to get from here the title and IMDb rating, I could go into here and grab title, and in addition, IMDb rating. We need IMDb rating from it now. So let's go grab IMDb rating, which is all just NAs anyways. Rating IMDb. And we go right here, drop it in. We should have it. There you go. There's just many ways to do things. And there's no wrong way. There's just different ways. So look right here with this code. Line 74 finds which rows are missing. Is it NA from this vector? Well, where are the positions? Store those as rows. Now go to the movies data frame, bring those rows to me, and also the following columns. So now we get it. And we could also then go in here and save it as movies ratings missing, or missing ratings. And we basically replicated the task. Both ways take a moment. And since this is a small data frame, sometimes it's quicker to do it by hand. Now, what you'll notice is down here, we actually have the missing IMDb ratings. So we can actually put these back in because we don't want there to be missingness with our data. So let's go right here and get our movies right here. We're going to join them with these missing ratings with a left join. So we've got the movies and we're going to store into it the movies, but we're piping it through a left join. So watch what happens right here. We run just this line of code right here, and you can see what we get. We get the following. Over here, you can see we're joining in the IMDb rating system. Let's clear the screen and run it again. We're going to join in the missing IMDb ratings so that if it has it, it's also going to be brought in. We're going to mutate the IMDb rating, if else, if it's missing, and then the missing rating right here. Let's read through this a little bit slowly. Going to mutate, which means we're making a new column in here, IMDb rating is going to be the column and the if else right here. So if it is missing, if IMDb rating is missing, then input the missing rating IMDb, else use its rating. Let's repeat this line because it's a little tricky again. Mutate creates columns inside of here, and we're mutating the rating IMDb column, and we're saying run the if else. So this is the logical part of the if else, where you have a logical test. If it is missing, the IMDb rating, then you will use the missing rating. But if it's not missing, you'll only use IMDb rating. And if else has the following format. Inside of it, this is the logical test. Then over here, you have if true, do this. And then over here, you have if false, do this. So once again, make sure you know the formats of an if else, that you're running a logical test. This portion of the code runs if it's true. This portion of the code runs if it's false. And technically, this whole thing right here is the logical test. So the first thing there is the logical test, which it was testing to see if it was missing. This code runs if it's true. This code runs if it's false. And then also we are removing out the missing column from the join. So let's go ahead and run this as I backspace through this. And let's run and store into our movies. I think it's mad at me because I've been running this a few times right here. Let's rerun it. There we go. I basically messed up the movie's data frame by running into it and joining it multiple times. It had columns it didn't want. So be very careful, run all your code in order. And if you notice the trick I did, I went over here, reran all code above. Everything I've written above is correct. I've created a data frame that has the missing ratings. So I can join in those missing ratings into the ratings that don't exist. So I needed to go here with the correct missing ratings and then have my movies data frame that I hadn't made mistakes on yet. Running all the code above just reruns everything I've done above that is correct, and then run current chunk. And now we have it. So now the movies have the ratings there, so we're good to go. And we can do a check for sanity. We should get 0. We got 0. Once again, this is the same code we saw earlier. Is there any missingness in the movie ratings? And find me the sum. Once again, this will give you trues and falses. Trues and falses are 1s and 0 in the brain of R. And with that, you can sum these up. And if there is no missingness, you should get 0. One fun check to do is actually to do an is.na on the full data frame. There's 103 missing, but it's elsewhere. Let's go take a look. Find the most commonly occurring value of ROI. So with this right here, we're using these pipes to pass it off to the next stage. Movies is being passed off to group by ROI. Next, we're going to summarize a count by it, arrange in descending order, and then show the start of it. There you go. The most common ROIs are right here. -1 is the most common ROI. 14.5. What is getting 14.5 ROI? But a lot of movies have -1 ROI. Did they lose all their money? Very interesting. So we need to investigate a little more on this. What's the pattern we see here? What do we think? Well, there's one big ROI that jumps out, the 14.5, and frankly, kind of want to find that. So we want to look for these movies, first off, that have the -1. We can go further and look for these 14.5 ROIs, but -1 occurs 62 times. So the filter right here is just going to filter down and give us only the movies with an ROI of -1, and then we can see all the titles. All the budget, excuse me. And here we are with the budgets. Whoa, they lose all their money? Here we go. Title, 22 bullets, 22 of July, 47 meters down. Weeks of the month, the 5th week, the 2nd week, the 3rd week. Try to see if I see any movies I know in here. I don't know many of these movies. Those are big budgets. Exactly. If you pursue ROI analysis, you need to keep this in mind. So here's the issue. Is this accurate? Did these movies lose all their money? I don't know. Looks like there's some issues with this right here. IMDb rating, ROI is -1. And the budgets for these, that is a lot of money. My gosh. You tell me that movie lost 150 million? That's row number 4? What movie was that? 6 Underground? What movie is that? 6 Underground. Box Office Mojo. Here it is, 6 Underground Box Office Mojo. So it is from when? Apparently it didn't do so well. 2019. Is that Ryan Reynolds? I don't know about this. It looks like Ryan Reynolds to me. Is it right? Is it wrong? Is it misentered? Bit concerned right there. 150 million. And I don't know of it. So let's go further right here. Let's look at the missingness right here. And for each of the columns. Remember how I said there's 103 missingness? Well, the column sums is going to do it by each column, which is a much better way to investigate the missingness. Rather than going through each column individually, you just see it done at once for you right here. So now you can see where the missingness is, and it's on secondary genre. Is that a problem? Oh, not every movie has a secondary genre. Some movies have 4 or 5 genres, as seen by number of genres. So I would say not as big of a concern here that we have missingness, because every movie should have a genre, but not every movie is going to have a secondary genre, like a comedy romance comedy, rom-com, that's what they call them. Examine and get to know what the main genre column is. What is some cleaning that needs to be done here and why? Now, the issue we're going to run into with a lot of these, and I always like taking a look at them first, is doing a summary of these columns. If we do a summary of movies and go to main genre, oof, look at this. We got Western only has 4 right here. Mystery has 30. It's over my shoulder. And history only has 8. So we have ones with only a few levels, and we get a much better analysis here if we do it with the code. Summary is just nice and quick. You can see the descending order right here. So that code I just ran, which I'll show again. If you watch the steps right here, movies grouped by the main genre. So that way when we summarize by the count of observations, we can see it. The reason you do the next step right here, pipe it into the arrange in descending order, is making it much easier to look at. And last but not least, you could do something where you do a head and do the top 10. So we also want to look at some of the lesser known categories right here. So it's not always needed to show, especially for something with only 17 levels. It's a good idea to get an idea of what the small levels are, the ones that are not as common. And this is where we're going to use one of our functions right here to replace the rare levels. If you notice what we're doing, we are mutating the column that we're working with, which means we're going to write into it. Mutate creates columns or can write into columns. So we are going to store over the movie's data frame with a version of the movies that has been piped into a mutate. So the mutate is going to mutate the main genre column. You can call it a new column if you want, but I'm just going to keep it to the original name right there. The replace levels function is going to do it on the main genre vector, and the threshold for replacing is 29. So now let's take a look. I like rerunning code right here because I like seeing what it did and I like analyzing. Anytime you run code, you should be like, what did I just do? What did I just do? And what we should see here is rare levels have been replaced. And there you go. Rare levels have now been replaced right here. You notice the other group right here. So we now have less levels to deal with. And this can really help working with data that has tons and tons and tons and tons and tons of levels, because you don't want to deal with something that only has like 1 or 2 instances. You can't get standard deviations from that, from 1, because mathematically 1 point has no variation. So you can't calculate standard deviation of 1 observation. So you can't even run a lot of statistical tests. It causes problems. And the other group is probably going to be one of our higher variation groups because it deals with a lot of groups combined into 1. So right there with the data, we now have something a little bit easier to work with. I think we went down from 17 down to 13. That's better right there. Now, secondary genre, let's see what we got going on right there. So first off, let's take the same code we have previously, just run secondary genre through it. One of the things I really like about dplyr is with dplyr, you actually get the autocomplete inside of your functions versus when you type a vector and you're doing it just in the global environment, you don't get autocompletes. So here we go, same sort of thing. We got Western and we got NAs right there. Nice that the summarize reports it that way. You can see the common versus the not common. Western, music, war, romance. So we do have a lot of levels not as reported. So now we're going to go right here, do the same sort of thing right here. This time though, we are taking right here, we are mutating secondary genre, factor NA to a level, and we're calling it none. So this way we're replacing the missingness of the secondary genre with none, and we're adding a level. This is an issue that when you have a levels vector, Let's go look at that. If you have a levels vector for the movies and you have secondary genre, the levels vector does not have a value none. So if you try to write to the levels vector and you do something like none, who's a bad idea. It should just get mad at me. Yep, it's mad at me. Hopefully I didn't break it, but it doesn't like that. Okay, good, I didn't break it. What you have to do is you actually have to add a level to the levels vector. You can't write in a level that doesn't exist. You have to create that level in the levels vector. And that's what you see right here, factor NA value to level. And it's going to find the NAs and create the level none and do that for us via what you have to do inside of R. Then we're replacing rare levels for things under 18. So down here, war, music, and romance. War, music, and Western will be removed. And we will now have none with 103. Let's check our work and see if we see 21 for other and none with 103. And there's none with 103 and 21 with other. Once again, a lot of this could just be done by hand if you have to correct data. But this is why we code, because it's like, okay, I want those to be other. I want this called none now, which kind of makes sense. There is no, like NA is fine too-ish, just depends on some algorithms. But it makes sense more times to say there's no secondary genre and store that as a level. And then we could say, what does it mean if it doesn't have a secondary genre? So now let's take a look at some of the values. So we got main actor right here. And what I really like, and we're cleaning it all up down here. So before we clean it up, let's grab a little bit of this nice code right here. And one thing I want to point out is you can just turn this into a function the way I'm using it. Watch this. Let's go here to fun for function. F is for n who do stuff together. U is for you and me. N is for anywhere and any time at all. Teachings 474. And we're going to take and we're going to say variable. And we're going to go put our function inside of here and type variable. And then I'm going to say summarize movies. Okay, there we go. And now we go back down here and we go to summarize movies. You don't even have to type it in order. And can I do main actor? No. It doesn't have the autocomplete, but it should work when I do this. Oh, it's mad. Well, that was a bummer. I wanted to do something fun on the fly. Variable. It should have liked it. As far as I could tell. Should have returned it. Let's check. Variable not found. 2 seconds. There's variable. Movies. Group by. Well, I would have thought that would have worked. Because variable doesn't want to find the name, does it? Let's try movies. $, main actor. It's mad. Column variable is not found, so it's not replacing that? Should? Am I going crazy? Should have replaced it. Well, try to do something fun on the fly and R gets mad at you. You know what I might do real quick? We're going to cheat. We're going to go here to OpenAI in the other screen. And we're just going to say fix this function so it works. Because I really wanted this. I really wanted a nice clean function to do this. And so make this function work. Okay, that's not the function. Oh, that is the function, yes, good. It says the issue with your function is that you're passing the column name variable as an argument to group by, but it needs to be passed unquoted. You can use this to do it right here, copy code. So it's mad at me because it needs to be unquoted and it says do this. Wow, I've never done that. Okay. The things you learn while doing code. Now will it autocomplete? If it autocompletes, I'll be very happy. Nope, no autocomplete. That's not a good sign. But it runs. There you go. So the issue was your function, you're passing the column name variable as an argument to use by group by IAM, but it needs to be passed unquoted. You can fix this by using bracket bracket to handle the column name properly within the group by function using tidy evaluation from the rlang package. Well, I wouldn't have known that. I was like, this should work. That should work. I'm just making this function to work with this data. The main reason I'm doing this right here is I can now take these and just toss all of these inside of here and get my nice neat tables. I could have just copied more code, but I wanted to play with functions. And you can now see, here we'll just run all of them and take a look at all the output. And let's take a look. So here we are, Nick Cage in a lot of movies. Oh, where's Nick Cage? He's still doing stuff. So Samuel L. Jackson, Dwayne "The Rock" Johnson. And then we've got main actor tomato meter right there. Frank Welker, Samuel L. Jackson, Bruce Willis, Michael Papajohn. Who's that? William Dafoe, good stuff. Warner Bros., big studio, Universal, Columbia, Walt Disney, Touchstone. They don't do much these days, do they? And last but not least, the main director, Steven Spielberg, Ridley Scott, Tim Burton, Zemeckis, Ron Howard, Michael Bay. A lot more from him these days. So a lot of good stuff right there. Lots of different answers. Now, the problem we run into is the following. There's a lot of actors. If we look at the tail of these, let's go back up here and change this to just the no range, or put it in just a range right here. Watch this. It's gonna now be the people we have not seen that much in here. There we go. So now when I rerun this, we get Aaron Eckhart. Wait, he's only been in one movie? It's the guy who played Harvey Dent, isn't it? What's he doing these days, Aaron Eckhart? Yeah, Harvey Dent. He's been in a lot of movies. Hope he's doing well. So Aaron Eckhart right there, Harvey Dent, a lot of other people I don't know. Adam Driver, he's been in more. Anyways, so that's why we're sorting it, but apparently the movie data frame does not have a lot of Aaron Eckhart in it, although we wish it did. So we're gonna do the same whole replacing rare levels here. And you notice we're just doing it for all the columns. So bada bing, bada boom. Rare actors have now been replaced. And this is kind of a bummer, it makes me a little bit sad, because now I'm guessing at the top of every single vector, what are we gonna see? I think if we have a lot of rare actors, when we go back through here and run our function again, what we should see near the top is other. It's a lot of actors replaced. A lot of directors replaced. And that's exactly what I thought we'd see at the top. So just know what you're doing. It's all right. The thresholds just depends on what you want to make them. This is where there's all models are wrong. Some are useful. What is a rare threshold for each one? You want to look at the data and think, okay, at what point do we call it and say, we don't want this to be a level for an individual because maybe there's only 2 observations for them. So it really depends. Notice how main director went down to 12 and we really only have, might not be any others. Yeah, there's only 8. It's only 8. There's only 8 directors in the world if you didn't know that, only 8 directors. So it really can change up how things are going depending on the threshold right here. Just depends on what we get. Let's continue on a little bit right here. And now we're going to change the MPA rating right here. And if we have an unknown, or if we have the blank blank, we're going to put it in as unknown right here. So the problem is we did have some of these MPAA ratings. Let's go to movies and MPAA rating. And notice right here, there are ones with just a blank inside of it. And a good way to view that is once again with the summary. And there we go. A lot of people don't know this, but this is just blank blank. That's all it is. And I wish you saw it a little bit better. It's just that it doesn't put quotes around the words, but this right here is this. That's what the level is. It's very hard to tell, but that's what that is. Technically, and I will say this too, sometimes you get some of them that look like that, and you don't see anything inside of it. So it's really a pain sometimes dealing with those. Don't like it, but we're going to change this to unknown. And now if we go back and summarize, we know we've cleaned it up with that. So you have to think, why am I doing each of these things? Well, you want something to be displayed in the MPAA rating. If it has a blank like that, you could turn it into missingness, but that wasn't missingness. That was the vector, a quote with nothing in it. So that's messy data right there. That is not good. Here we go. Let's look at the NAs now. Oh, good stuff. So if you notice, we no longer have NAs right there. All the NAs have been moved. Secondary genre has been fixed and cleaned. And now we need to save our data here. So what we're going to do right now is we're going to write this file to our computer. And I do want to point out at this time that if you ever want, you can use the read Excel package. Nothing wrong with read CSV. I do like read Excel. And you can read Excel files. Should have it on this computer here. And then you can also do write Excel. No, where's my read Excel? Write.excel. There we go. Really? I thought it was write Excel. XLSX. No. Write Excel CSV. Oh, there you go. Let me look inside the read Excel package real quick. And then, oh, I was doing write. Oh, you can't write Excel? You can just read Excel? Well, there you go. Still have to write CSV files apparently, but write Excel. I'm not even kidding. Write Excel. So there's a read Excel package, and I haven't written an Excel file in a while, and there's a write Excel. There you go. So if you want to write Excel files, you have to, there you go. There you go. Now you can write an Excel file. So technically speaking, and I can't remember if it includes row names or not, you could go right here and make this an XLSX file. And it doesn't like the row names part of it, so we can remove that. None of these ways are wrong. What's it mad about? Unused argument. Oh, I think it's because it might not call a file. There we go. It's just different structures. And now I have both these files on my computer right here. Write Excel writes it as an Excel file. So the file extension needs to be Excel. And read Excel writes it as a CSV function, or read CSV, I meant to say, writes it as a CSV function. So write writes files to your computers, read reads them in, and of course the read Excel file package reads in Excel files. So if you have an Excel file, you can just do read XLSX, and then you can just read in an Excel file with that and give it file name .xlsx. So that reads the file from your computer, and we can just hashtag that out right there. So let's take a look a little bit at this main driver analysis right here and figure out what is a success. We've got our movies read in. We can just reread it in now. It's just going to overwrite what we currently have because we've stored it to our computer. And this is really good if you want to come back to this or send somebody your file. They're just going to get your movies file that you have. And especially if you're working on a team, you might want to clean up the data and say, hey, the data's all cleaned. Here's my file I used to clean it up. Do you see anything? And tell me what you think. Now we're going to take away ROIs that are too low because it kind of gets iffy because we had a whole bunch of those -1s and it's kind of weird. Ryan Reynolds had a bomb of a movie. I don't think so. Not in my world. So let's go right here and filter out the ROIs that are greater than 0.95. So now let's take a look. Here we are. Now we have only the ROIs that are greater than 0.95 negative. So we did move down, and if you watch the size of the sample, 2,147, and we lost about 70 movies. So right here, what you could do less than equal to, and call it movies 2, and there's movie 2. So why did I do that? Really quick way to see that we have lost 78 movies. And they could find out which movies they are by just taking a look over here and seeing a lot of the same movies. Some of the ROIs are movies that we had talked about, like the SpongeBob, Sponge on the Run. Well, it's not the first SpongeBob movie, so that's why. First SpongeBob movie is much better. How can you define success for a movie? What are different factors at play? And this is where you come into play, especially with case 4. So this is a good time just talk about with case 4. You want to be thinking about what makes a movie successful and going off of what you think the main drivers are. You're meant to communicate these things and be able to work with data, sort through it. We're here to just take the knives and forks to data, cut through it and find what's good and deliver it to people. Maybe we should just give them the plate of food. Well, we're here to make the food and deliver it to them. So maybe right here, aim for 15-20% of items being successful. What is a good way to start a value of success threshold? You don't want to call everything a success. I mean, we're positive here, but I don't want to say everything's a success. Let's go for the cream of the crop, take the top 15-20% and say, this is what we want to aim for. What does it mean to be a success? This is the hardest part about analytics because you're trying to gauge something and then figure out how to replicate it. Like, what is the success? How do we get there? What are the main drivers behind it? So let's create an outcome column here that has the value success when movies meet our criteria for success and has the value failure when they don't meet that threshold. So now we're creating a categorical Y of interest to which we can analyze this. So here we are with code to modify. Don't use the same exact code, but look right here. It's a don't modify this code, modify this code. Don't modify it a little bit. Think about what a success means to you. Modify this code. It's an if-else column right here, creating a new vector onto the data frame. We could also probably use mutate. I'm gonna try a little mutate by hand right here. So we're gonna go here to movies, and then we're gonna pipe it through. That was Control-Shift-M for quick. We're gonna mutate. And we're going to mutate an outcome column onto this, which has an if-else. And the if-else is going to look at it's basically just the same thing. Why don't I just copy this then? See, sometimes it's quicker to just write it there. Does it like it? Yep. And then you know what we got to do? Got to go in front of it, and we got to go right here, English failure, and then rerun it. So it is kind of quicker sometimes, or well, the end of it is what we want to look at, or and actually there is one issue with this, I will say. It's a character right now. So with it being a character, we're going to go in front of the mutate, and let's go factor, and that should do it. There we go, and that should overwrite it. So we see right here, outcome, and outcome is now a factor. Good stuff. So notice what we've done right here. We've stored a factor, which is a categorical variable with the outcome, letting us know whether or not it is a success or not. We now want to predict success on only factors known before its release. Because think about this. If you know a movie has a high ROI, you already know it's a success. This is a very common mistake out there in the real world, because if we don't have the X's that we know, we can't make predictions. If we're predicting on ROI, well then ROI, it just tells you what success is. It's very correlated with success or associated, because it's not success being categorical. We wouldn't quite say correlation. What predictors are needed? What does success look like right here? So movie title doesn't really contain much unique information. Now, I will say this. There's a really cool function. And what if we use what's called grep? And I'm trying to remember this function, but this is kind of neat things. It looks for patterns. So grep, we could go through the patterns in title, and we could ask for the pattern the. And I'm pretty sure it should find. No. Let me say modify this code so that it finds modify this code so it does a search through the vector and returns true or false if it contains the word the. Okay. grep should do it. Grep kind of searches through strings, and I'm of course cheating a little bit with ChatGPT, and it's the goes first. I made a small mistake, and it would be this. So I'll show you right here. It's grep L, and now we could do like returns. And how many have returns in it? So let's find out a word that is common. This is me kind of thinking through what it might be. No returns. Might be a capital R. And I think there's a way to do it so it's not case sensitive. So let me say, modify this code so returns is not case sensitive. Modify this code so returns is not case sensitive. You know what? There's so many Batman movies. Only 8? There's only, oh, it has ignore case. Yeah, so it's just ignore case. Superman? Spider-Dash Man? 9 Spider-Man. So, ooh, Marvel. It's not going to be Marvel? Marvel? One Marvel movie. So, what you can do with this right here is with the trues and falses from this, you could use this in an if-else. You could go here and say logical test, store it as your logical test, and then go in and create your new column. So we're going to go to movies and say Spider-Man, and store into Spider-Man, if-else, and logical test. And with logical test, I misspelled over here. Logical test, and we'll say, oh, we need to throw inside of a factor. This is going to be a categorical variable. I'm doing my data now. And logical test, and we'll put here yes, and we'll put here no. And now we can go find our Spider-Man movies. If we go here, especially, you can just sort the vector. Nice and easy. Spider-Man. And here we are. Here's the Spider-Man movie. Spider-Man 2, Spider-Man 3, Spider-Man, Spider-Man Far From Home, Spider-Man Homecoming. Into the Spider-Verse, Spider-Man No Way Home, Amazing Spider-Man 2, Amazing Spider-Man. There you go. There's the Spider-Man movies. We all know them. We all love them. And there they are. So rather than going through individually and finding them, you can easily find things. grep is one of a really cool function we haven't used in a while. We had a Delta dataset with tweets. That was a fun dataset we did a long time ago with grep. So think of some fun, cool things you can do. I don't know. I just want to throw a little bit of my flair in there. We'll move out title now. Bye-bye, title. It was very nice seeing you. When you store the null object into something, it goes away. Bye-bye ROI, bye-bye rating, bye-bye rating, they're gone. So we've removed out those things, and why did we remove them out? Well, title we could do fun stuff with, not a bad idea, but title has so many unique levels that unless you're doing things like I'm doing where you're creating superhero movies, you're not really going to get a lot out of it because way too many levels. And having another category, think about how many movies have the same title. Very few. We could have checked that, but very few. Next, we have ROI because we're not going to know that when a movie comes out. Next, we have the rating. Not going to know that before a movie comes out. And rating, tomato meter 2, not going to know that before a movie comes out. So now we need to make a decision tree right here. Now, with this right here, a decision tree can handle numeric and categorical data. And we'll be able to make interpretations by the way the tree goes. So when you make a tree, basically all your data starts at the top, and then it splits based on a decision like, what is its budget? What is its genre? And then we can kind of look at whether a movie was a success or not based on these factors that we would know beforehand. We have here the complexity parameter, which is basically how the tree will split. When we have a lower complexity parameter, we allow the tree to split more. And when we have a high complexity parameter, it needs to have a big return to split. So this is something we tune on. Tuning is like where you have a dial and you're trying to get things to the right frequency. So tuning your tree is trying to optimize it so that you get it to split the right amount. What's the right amount to split? Well, we'll see how the data looks and how it does. So do we want a high tree, a high complexity parameter? This will have fewer splits because we're making it very hard for the tree to split. And then if we set a low complexity parameter, we're like, if you do anything better, anything you can split. The way to think about complexity parameter is when you have a high parameter, you're asking a lot of it. And if it's going to split, it's going to do something really awesome. And when you have a low complexity parameter, anything you do, I'm like, yay! It's very low bar for it to go over. So think of it as a bar it has to get over in terms of doing better. And it's very hard to go over the high complexity parameter bar. So finding the right amount is tough. The min bucket is going to be the min observations in each leaf. A tree has leaves, even though the tree usually goes downward when we see it. If you flip it upwards, it would look like a tree flowering out or a bush. And with that, this is the minimum observations. And if you have a lower amount, you can get more splits because the lowest amount you could have is 1, and you could just allow the tree to split. And if you put the complexity parameter very, very low, you would get this humongous tree, which is probably very overfit. So you have to watch out for things like that. It's finding the right amount of observations in each leaf, min per bucket. The bucket is a leaf, basically. They're just calling it a bucket here. And the right amount of complexity parameter on the return you have to get to do a split. And there's just a lot of ways to do this. Notice right here, we have the arguments. The minimum observations per bucket are 100, and the complexity parameter is 0.01. And I'm going to pull this over here. I'm going to say, use Taddy models and make a expand grid that does 100 different trees and does it more complexly. Never be afraid to use AI. We've got our tree right here. And there we go. Now let's look at what we have coming out of the AI. I do love throwing in some AI, especially with what it can do. We're getting the AI's response over here, and we'll take a look at what it has. And it's setting a seed so we can get the same things. And I'll copy the code over and we'll take a look at that. And then we'll take a look at our tree. Okay, so I'm going to copy this code. And let's go here and go to insert chunk. And we'll say AI tree. There we go. And did it visualize the tree? It might have shown the tree. We'll take a look at that next there. So here's the complexity parameter of the trees it gave me. So it has 2 different trees right here, a complexity parameter of 0.0244 and a complexity parameter of 0.01. And this tree did not split. So what does it mean when a tree does not split? Ooh. And a tree does not split. You don't get much anything. So this is a 2-split tree. Why is it a 2-split? Split 1, split 2. Notice how 2 splits leads to 3 leaves. If we go back up here and set the complexity parameter higher and ask more of it, we should get a no-split tree. So now it's probably not going to split, or no, it did split. I'm going to set it about as high as this and try not to get it to split. Ooh, let's set it high enough it doesn't split. Sure, now it shouldn't split. There we go. There we go. There you go. That's a no split tree. This is non-informative. This is a no split tree. It really doesn't tell you anything, and that's why you got to watch with the complexity parameter. Once again, we also do want to watch if we set it way too low, we could get something crazy. And just showing you the different sort of ideas you could get right here if you allow your tree to do things like this, and it's really mad at me. So once again, the idea of a tree being junk is a problem if your tree is like not interpretable. I said you can just put one observation and split all you want. So now we got a ridiculous tree. Don't do that. You want to figure out the right amounts. And this is the kind of art to it, because it can be very hard to figure out the exact amount. And I've also got some advanced code we're going to look at here in a moment. Let's take a look at this tree that is not crazy. And when the budget is greater than, I think that is 20 million, then you notice right here, we go to the yes. So the way this is read right here is budget greater than 20 million. Yes, go left. Success right here is 12.7%. And now notice the highest success is actually over here. Because remember, we're gauging it by ROI. So these are like big blockbusters. There's 17,000 movies almost over here. That's what the N represents. And a lot of them were failures. The best rate of success would be going down this path right here. So what do we have? We have right here, was the budget greater than 20 million? No, greater than or equal to technically. And was the main studio, whatever these are, that's Lionsgate maybe, MGM, all these studios, WB. If it was not those studios, you're over here. So the formula for success is based on smaller budget coming from a studio that is not these. We could also make a list of these. So another good thing to do would be to go in here and identify the studios that are not in this list. And so those would be the studios we would expect to have a higher rate of success for low budget films. So right now, what I'm learning from this is low budget films from certain studios do really well. It's probably why they bring a lot of them to the market. So they think low budget from certain studios, great idea of success. I'm gonna take a look at this advanced code really quickly right here. Let's see, my first time seeing this. We're running tidy models, which we already have. Oh, we hadn't loaded up yet. And now we're setting the seed for reproducibility, meaning that we can redo this again. We've got right here, the complexity parameter is going to be tuned. Are we putting it in? Are they putting it in? Well, let's run it. There we go. It's going to tune it for us, is it? It's going to tune the complexity right there, and then the minimum nodes and the rpart engine, and we're doing classification for categorical. The tree grid right here has a size of 100. That's what I asked it for. And entropy is going to be lossage, and we've got right here, that's what it's going to tune on, is entropy. Okay, there's my tree grid. Let's look at it. Did it not sort? Oh, there it is. So interesting values on the minimum observations in a node. And now it's doing cross-validation to make sure it works correctly. That ran. It's now running my model and predicting the outcome. It's now tuning my tree and finding the best tree. And then we're going to show the best tree. Use the rattle package to visualize the tree. And this might take a moment. Okay. We'll give this a moment more. I'm also bringing in the rattle package here. It's got rattle and rplot. We'll bring in this code and we'll hope this runs and doesn't take an hour. Rattle has really nice rplots and has fancy rplot. And I can just tell it to do the tree. Oh, it ran. And let's take a look. Show best. Those are the best trees right there. Cool. You can see the complexity parameter. And the minimum nodes is 5. 5 is very tiny. I'm a little bit afraid of these trees. Well, let's see what AI did. Because we got our tree tune right there. Is that going to run in the rplot? It doesn't like, oh, it could not find function. It's in the rattle package. Let me put the code in order. Nope, don't restart my R. And let me load these libraries. lib is a shortcut for library. And library. It doesn't like the tree. Oh, it wants... Is it just grabbing that? Let's go to our tree. There's the tree we made with Petrie, I believe. Yep, 3 leaves at the end. And actually, Petrie's tree might even look better. This is the fancy R plot from the rattle package. It sometimes looks better, sometimes looks worse. Due to the amount of studios right here, it is pretty crazy to read. And I'm going to try one last thing over here and say, I'm going to say create the best tree from this output. I'm giving it this output right here and saying create the best tree from this output. And so I just want to see the tree it gave me, because it gave me the tune grid showing me the best tune for the tree. And the best tune for the tree is this. So frankly, we might have to go in and do it manually here, or actually best tune should be able to take from the tree tune. Well, it doesn't show the best tune right there. We might have to manually enter it in, but I'm a little bit, here we go. Final spec. Okay, so let's see if this works, and then let's continue on looking at our tree. We're almost done with this lecture right here. So here we are from AI. There's the code right there. And workflow, best params not found. Oh, because up didn't save the best parameters. So remember how I was looking at those parameters for the tuning? It's going to store those parameters right here. And it's the parameters we saw, 0.0196 and 27. There it is. There's the best parameters. Like I said, I could manually enter those in. Now it's going to get the tree specs, make the workflow, a lot of tidy stuff right here, fit the tree, and load up the rattle package and make the plot, and it didn't do it. So that is a bummer right here, because we should have the tree, and that looks like a crazy tree. You can actually see the tree, but it's not visualized right here. It first splits on budget and gives you the percentages, but it's a bummer to me that this is not visualizing, and that's sometimes what can happen. Ooh, Petrie's is doing it. Or I should have just done it over here. It's going to be a mess, isn't it? Well, ooh, Bruce Willis, there you go. And Brad Pitt. So here's the issue. When a tree gets too large, you don't learn as much from it. So as much as I love AI, I think our non-AI was better. Because over here, you can't really see what's going on with this tree. Let's look back again what we have in the notes. This. Pretty easy to see. I know it's a lot going on right here on this split, and it's going over that leaf right there. So if we make it bigger, it's a little bit easier to see. This isn't the prettiest. I might try to pretty it up and maybe show people what's going on right here with the failure. And I think if we redo it, that line will be full. There we go. And we can better see here where the splits are happening. So once again, you really want to watch out, because if you start turning in things like this, it might be hard to read, even though it's a little prettier, but you can run into issues with what you create. So be very careful. Endowed plot. Be very careful. I love AI, but not always going to give you the best answers, when sometimes the easy way is the best. So here we are with a more complex way right here, setting our complexity parameter to 0.006, 30 per bucket, and we have here the movies data set with the equation we are using. So what does this mean? Outcome is explained by the following X variables. This is the first argument right here. Then the second argument is the data it comes from. Next, the minimum buckets, and then the complexity parameter. So what we can do now, nice and easy, is visualize the tree. Visualize model right here, tree. And as you can tell, we got a much bigger tree, allowing for those buckets. And let's see, can we actually read it? It can be hard to read. I think maybe, let's see what Fancy R Plot does with this. Ready? No, too small still. Too small. Let me try and make them bigger. Okay, get it sized right. Not too bad. We can actually see it now. So if you look right here, budget greater than 20 million. Failure is a little bit higher. I'm going to look down to the most successful movies. Looks like right over here. Ooh, look at this. These months. April, December, February, January, July, March, September. And that's if it doesn't come out in those months. So this would be, no, it did not come out in these months, and it did not have an R, other, or not rated. So right here, you've got the ratings. Is it not those? So cheaper movies with not these ratings that don't come out in these months. So you'd have to figure out what the other months are, but that is going to be kind of your recipe for success. And if you notice, genre doesn't happen till the end. The most successful movies, and these are only 65, so I'm a little wary at that. There's so many movies over here, though. I really wish we had broken down this further, but the algorithm didn't have us going in that direction on this. But it does seem to me that there's things at play right now, and it could be interactions between these. Like maybe R-rated movies are better to come out during a certain time because you notice R-rated movies go over here. Is the MPAA rating R? Then it would be over here, and then we'd look at the high success over here, and it would be it did not come out during these months, and the secondary genre was not comedy, not history, not horror, not not romance, not sci-fi, and so those genres that are not contained during not these months that are R-rated movies would have the highest probability of success. So understanding how to read these plots and know what they mean is very important. I'm going to ask one more thing of this right here. I'm going to put this in the... One thing I like to do is I'll put it as a comment right here. Save a vector of predicted probabilities to my movie data frame. So right here, we're going to get the predictions from the tree. And so we should get, here we go, predicted probabilities. It's just classic prediction code. And there we go with the predictions. So I think I broke something though. Let me be very careful. Let me zoom out a little bit here. And there's the code. And so we're predicting, I'm going to predict from my tree and new movies data, the original data, type probability. And there's the predictions of all the predicted probabilities. And then we're going to take the outcome we care about, which is the success right over here. And I believe that is the lower column right there. So success. So I might even write my own code right here. I'm going to go to predicted probabilities and go to success. Oh, because it's the way it's formulated. Yeah, the way it's created. Nope. Predicted probabilities. $. Success. That's that. And let's go to column 2. There we go. That's column 2. And then let's save this right here. And what I want to see is I want to go to my movies data frame and just look at this now and see which movies have the highest probability of success. The highest probability of success is, oh, we took away the titles. No. Darn it. Oh, it's these movies. Oh, we have to figure out what it is. It's original row 28. Original row 28. We should go find out what that is. Original row 28 and 94. Row 28 and 94. We'll find that out here in a moment. But these movies have the highest probability of success, and then the lowest probability of success is down here. Yeah, so I might even, you know what I'm going to do? I think what I can do, and this, there's one thing I got to remove. We're almost done with this. But I really want to know the names of those movies. So what we need to do is we need to go where we nulled out title. And we need to hashtag this. And then I think with our trees, the problem is we have title in here. And so we should be able to go minus title. And we want to put this into all of these now because now we don't want to use title, but I really want to retain title. And that's good right there. That's the R part. We're fine on that. I need to also remove the code that took a while. Oh, we're way down the code. Where am I going? Oh, it already... Good. That's good. Oh, no, that's where we nulled out the first time, so I don't want to do that. And then now further down, here's where we did the crazy tree tune. And with the crazy tree tune, I'm going to remove a lot of this for the moment. Good. Okay. And that's where we're at. So we should be good if I rerun all this. I think we're good. And now we rewrite the probabilities to it. We save this. And now we look at the movies. Yes. Highest probability of success. 47 meters down. All is lost. An American Tail. Astro Boy. Austin Powers. Conan the Destroyer. These are the highest probability of success. These movies were Bound to be successful. Were they? I don't know. Cool Runnings, Home Alone, High School Musical 3. Be interesting to start putting these together. All those aren't successes, but they were the highest probability of being successes right there. So we have the tree right here with the outcomes, looking at the complexity of it, just going down a little bit further with the code, visualizing our trees so we can see what we have. Oof, not a good tree. Not a good tree. You see trees like that, you're very unhappy. And the reason this is happening right here, and this is exactly why Petrie did what he did. Title not found, I think it was lowercase. No, is it not? There it is, minus title. Oh, I put the dot. Dot minus title. There we go. And that's where you can really run into problems. You can run into so many problems if you create a tree that just looks absolutely crazy. So with this right here, you want to make sure you understand what you're seeing. If you notice with this lecture that we've just recorded right here, you can do a lot of different things. But if you don't know what the code is doing, if you don't know what you're seeing, you're kind of stuck. So I hope this has been fun. I've had a lot of fun. I love kind of adding to it, and I love thinking what's possible. My brain doesn't want to stop at what's the code on the screen. I want to always do something a little bit extra. So until then, bye for now, everyone. Bye.